if you put a tiny little kitty inside there, the kitty's going to be okay. Yep, still Sunday Arvo. Righto, so now we're going to talk about the size and the direction of the electric field itself. So we're going to start with drawing some, wow that's bright. We're going to start with drawing some positive, here's a positive charge, and down here we're going to have a negative charge. Now, the analogy or the way that I choose to tell you guys to remember this is that electric fields are kind of, they're emos, they're a little bit unhappy with things, and they try and escape positivity and they try and go towards negativity. They just, you know, like having depressive personalities or something or other. So what we're going to do is draw these fields. Now they go out of positive charges into negative charges, or the way that the textbook will tell you is the way the direction that a positive test charge would go. So bajillions of years ago, whatever, people were trying to come up with conventions for directions and names and constants and all sorts of other stuff, units of measurement, and this was one of the conventions they came up with, that a positive test charge would travel in the direction of the electric field, not just any other random charge, because obviously they go in different directions. So here's a positive test charge, would travel away from our positive charge here, and it would go like this. So when you're drawing it, be far more careful than what I'm being right now. All of these lines are supposed to be equal in length and equally spaced, so you don't have a region of space around this thing, like out here for example, whoops, where you have more electric field just, you know, at the top right corner, for instance. That's top left corner. Not sure how this is going to turn out when you guys watch it back. Anyway, that doesn't exist. That can't happen. It's perfectly radial, like, see, perfectly radial. In the case of a negative charge, we have the exact same thing, except the lines are going inwards. Another thing that I've just realised that I'm supposed to be doing here, entering and exiting the surface of the charge. Entering and exiting the surface of the charge. I'm just going to do that so it looks like it. Entering and exiting the surface of the charge, and also at right angles to the surface of the charge. Alright, so wow, that looks shocking. Anywho, you can see that it goes out of positive stuff into negative stuff, so this is the convention. The size of the charge will actually dictate how many field lines you'll draw and roughly how long they'll be. So if I was to say, alright, well here's a positive test charge, and then there's another one over here, but this one here just happens to be double the strength, you would, you know, a couple of things you could do, draw the field lines significantly bigger, like this, but also have more of them. Alright, so this would suggest that this is a poorly drawn but stronger field than this one here. Okay. Now if a charge was to be placed somewhere in this field, it would experience a force, just like I said before, the direction that a positive test charge would go. Well, yep, cool. But if we had a negative charge here, that would be attracted towards this thing. So we have a charge that sets up our field, another charge here that has its own unique field around it. These two fields interact using Coulomb's law that I talked about in the last video, and those two things, you know, create this force. So the direction is denoted by which way a positive test charge would go. That tells us what the field's doing. And then we have the direction of a negative charge would be opposite to that direction. So a negative charge here would go out, this one here would go in its opposite direction to what the field lines would suggest. If we had a pair of parallel plates, so it's not a hollow conductor or a hollow plate, it's just me trying to remember what to do here. If we had two parallel plates like this, a positive one at the top and a negative one at the bottom, what we've got is, if you zoomed in on this a long way, this top plate here, you'd actually find these things stacked up against each other incredibly close. So if we were to have a whole heap of these things stacked up together incredibly close, all of these fields are going to be interacting with each other. So that one, and it's going to have this thing, it's going to have this and this and this, and you know, all of these other field lines. And these field lines, remember, vector addition, they interact, they add up to each other, add up together, and they end up causing the field to do this. Once again, go all the way to the plate, out of and into at perfect right angles. Just similar to what I'm doing here, not exactly the same. And we have a field that goes like this, so it goes from the positive plate to the negative plate. Remember, once again, the direction that a positive test charge would go. If I was to increase the potential difference of the voltage between these two, so I made this one like more positive and this one more negative, obviously that would result in us drawing a denser, tighter packed set of field lines within those two parallel plates. Alright, in reality, we can't have a pair of infinitely long conducting parallel plates because way too hard to make, and also infinitely long, come on, it's just not physically possible unless we're in magic physics textbook land, which is where we all live apparently. So what we end up happening is these parallel plates do have an end, so there is, you know, a finite length that these things are long, so they might be this long or this long or this long or this long, it doesn't really matter, but they have some sort of edge to them. So if we were to zoom in a lot, you know, this is that kind of right hand edge, and same thing with the bottom plate like this. So we've got a whole bunch of positive charge left over there. This one's, you know, overall negatively charged, but we've got positive charge stuff at the top as well, so it's all kind of spread out, and it's all, you know, it's near the edge. So if, you know, here's some near the edge, it's kind of like this, it's still building up, but these ones have, like, you know, fields that are going like up and out and all this sort of thing, and these ones are the same kind of deal. We end up having what we call edge effects, where they bow out like this. Okay, at each end. I'm not going to draw at the other end because it'll cross over this thing, and kind of ruins the not to scale zoomy thing. So we have these end effects. In reality, these, yeah, they do exist. They do interfere with scientific experiments, but we're not really going to have to acknowledge their existence other than to be able to, hey, look, here's a picture of it. Now, if I was to change change and talk about hollow conductors, a hollow conductor is obviously, you know, hollow. It's a conductor that's hollow. So think the domey thing on the top of a Van de Graaff generator that we've got here. So if we were to charge that Van de Graaff generator positive, it would have, you know, a field coming out of it. I really should have done this one way better too. Please take more care than what I'm doing. I'm just drawing random lines going out like this. So we have the outer surface has field lines coming out of it, but the inner surface also has field lines coming out of it. It just so happens that the inner surface field lines, you know, so let's do like that field line and that field line. Wow, that's terrible. I need to chuck this one. These field lines that are on the inside, you can see that they all kind of, yeah, they point towards the center, but they all cancel out eventually. So not eventually, pretty much instantly. So inside there is no electric field, and the way that you're going to remember that is if you put a tiny little kitty inside there, the kitty's going to be okay. If the cat's on the outside, it'll get electrocuted and it'll get a zap. But if it's on the inside, the kitten's going to be perfectly fine. Alright, now I'm going to change the shape of this thing so it looks more like what we refer to as a coronal shape, or a corona. So we can talk about corona discharge. So if you look at the sphere circle that I had, or these parallel plates, you can see that the field is you know, perfectly kind of balanced and spread out and even and all that sort of stuff. What I'm going to draw now is something more like this. So we've got a point here. Now, when all these forces are kind of pushing and whatever against each other, what the positive ones are doing is actually trying to drag electrons towards them. What the negative ones are doing is trying to push electrons away. Now, if you've got a whole heap of, you know, stuff trying to jump, like the force on the charges in here is away from the surface, is away from the surface, is away from the surface. But these ones further along here, you know, let's set them up so they're pretty even to start with at least. You know, give we go like this. All of these charges down here are applying forces on all of these other ones. Now the net force back on this kind of round, like the big radius curvature over here, is along the surface a little bit, but mostly trying to push it away from the surface. But this one here and this one here, so let's look at that one and that one pushing on each other. There's going to be a force that is perfectly out that way and that way. So if we look at where these vectors go, that's a little bit along the surface, kind of down, but mostly away from the surface. I can't physically throw it out, like push it off the surface. Here, that's mostly along the surface, a little bit away. So over, you know, we're talking millionths of a second, I believe it is, we have this build-up of, like, you know, all of these fields forces interact with each other, and they start pushing the negative charges around, or dragging the negative charges to places. So we end up with this really quick build-up of charge around here. So we have this really strong electric field around the points, not so much around, you know, here. The other way to think of it is like this. You've got 4 bits of charge at a big thing. There's a line connecting the two together, and we've got 1, 2, 3, 4 bits of positive charge on this one. If you were, you know, here the charges are reasonably spread out, so the field's kind of not as strong. Here the field is concentrated in a small space, so it's a lot stronger. It's not the best way to think about it. It's not the best analogy or the best sort of description, I guess, but it kind of highlights what happens at this sharp point. So we have lots and lots and lots of charge built up there. Then, in order to get this corona discharge to happen, which is the spark or the zap that you'll actually see come off the Van de Graaff, especially useful in photocopiers, laser printers, that sort of stuff, what you'll actually have is like air molecules. So H2O, hydrogen, so 2 lots of hydrogen, 1 lot of oxygen. So we've got, you know, this sort of water molecule, or we've got a couple of, like, you know, bits of oxygen, and or all of these other different particles that are sort of floating around all over the place. And this thing here is incredibly positively charged. Remember, the whole surface is, but most of that, a lot of that's concentrated down here. So these things kind of twist, and, you know, the positive bit starts to be more repelled by the surface. So now we've got this tiny, tiny, tiny separation of charge, where we've got the positive bit that's a little bit further away. I just look like a sad face, but where we've got the positive bit a little bit further away, then the electrons kind of close together. And because this is it's a reasonably strong bond, but it's nothing compared to what's going on over here. So this massively positively charged end, I guess, or build up a positive charge, build up a positive, so the electric field down that end. So I'm just cleaning stuff off. Will strip away these electrons, so it'll actually steal these things. So now these bits of water vapor, air molecules, whatever it is, they are now positively charged. Positively charged things near positively charged things will experience a force. Now these things disappear. They go away, they bump into other molecules and steal electrons back and all that sort of stuff. So this continuously happens. So this charge is built up via the power point. You know, it's a supplied charge to the Van de Graaff, or supplied charge to the photocopy or the laser printer or whatever it is, and it continuously builds up this charge at these sharp points. We're talking tens of thousands, hundreds of thousands of volts worth of build up of charge at these points. So the fields are incredibly strong, but they're also hidden away inside of machines, so you can't actually hurt yourself on them. But yeah, they're incredibly useful and incredibly valuable to society. And lots of things that we do with modern day technology is designed to actually shield from these coronal fields or electric fields, so that we can keep our really delicate electronics really safe, and all that sort of stuff.